stationarity means statistics that don't change in time. Then the contribution by Milli, stationarity is that triggered a lot of other contributions. I also made a contribution in 2014 titled Stationarity is Immortal, and I explain you why. It is important, anyway, to understand what stationarity means, because there is a lot of misunderstanding about it. So the first thing to understand is the definition. So it means invariance in time of probability distribution of extremes in this case, because we are talking about extremes, which means invariance in time of the statistics, which means invariance in time of the whole process. But remember, it is invariance of statistics, invariance of probabilities. It is invariance then of the model that we use to study the events. An important thing that is to be remembered, and the second issue that I would like to emphasize. So first issue, stationarity refers to statistics. Second issue, stationarity refers to the model that we use to study the phenomenon, not the nature, not the reality of the world. So it is an assumption that we make about modeling, because it doesn't have any sense to say that nature, the real world, is stationary, because stationarity means statistics. And the real world is not a statistic. And the real world has a unique trajectory. So it doesn't have any meaning to say the statistics. It is only one unique trajectory. And if somebody says, yes, but I can take the trajectory and compute the statistics over a piece of trajectory. Actually, this is not really correct, because in any way, you are already applying a model. So you are saying, okay, I select a window and I compute the average during this window. It's already a model, because you can't really define for the real trajectory of nature what is the average. Because, I mean, today there is this weather, it's only today. So we cannot say the average weather today is, no, it's only today. If you use a model, then that's fine. If you use a model like, I assume that the mean value of the average of the weather today can be computed by taking the average over the whole week. Then you can say the mean weather today is like 12 degrees of temperature, because I took the average over 1 week. But this is already a model, which is a schematization that we make of reality in order to make a design. So just keep it in mind, because it is erroneous to say that the Po River is stationary. What is correct to say is the Po River can be described by a stationary model. It's a different story. And of course, some people, when I discuss these issues in conferences, say, yes, but it's important to deliver the concept. And stationary, if I say that the climate is stationary, I deliver the concept. My reply is, yes, I understand, but why don't you say that the climate is not changing there? Why do you take a term, a terminology that refers to a very precise scientific definition to mean something that is wrong? Because this, unfortunately, then makes everything difficult to understand. So we have to keep in mind that stationarity is something that belongs to the statistics, to the statistical modeling. We can use statistical modeling to deliver an interpretation of climate change. And then we can say that the model that we use to represent, to study climate change is stationary or non-stationary. This is why I wrote stationarity is immortal. Stationarity is an assumption. So we can make it or we can remove it. It's no problem. But it is an assumption, and in some cases, as I already emphasized to you, this assumption delivers more robust estimates with respect to non-stationary models. Anyway, let's connect to what we are doing now. Now we are doing an introduction to extreme value theory, which is extending what you already know. And we are working under the stationarity assumption. So we are working with data that we download over from the web, for instance, like we did for, I think we did an experiment with wave data or wind data, I think. We are downloading them, and they refer to 20 years, perfect. And then we estimate the average. And we assume that the average is stationary, because it applies to over the whole bunch of the 20 years. And then I make an estimate for the future under the same assumption. So it must be clear that what we are doing now is precisely this. And I anticipate to you that when we complete this, probably today, this discussion about probability distributions, which I don't want to extend too much, but on the other hand, we need to extend it a little bit. And when we complete this, our next target will be, okay, what about non-stationarity? So if I want to extend this probability distribution to a non-stationary formulation, how can we do that? Again, there is an extended literature, but we need also to discuss under which conditions this extension is appropriate, because it's not always appropriate. Even if we are conscious that climate is changing, there are several solutions if we want to take into account it, and using a non-stationary probability distribution is one of them, but not necessarily the most appropriate. Okay, now let's go to our lecture, Extreme Value Theory, which, by the way, I updated yesterday. Okay, sorry, I clicked on the wrong link, so it's here, teaching. Okay, actions, and then there is the link, Extreme Value Theory. Okay, now, just a very quick recap, where are we? So let me increase font and, yeah, okay. Okay, let's start from this equation. I cannot select it, so I select the row that is above it and below it. We said this equation is the basis of the block maxima method, okay? We still have to analyze the peak over threshold. We are still discussing the block maxima, and this equation is the basis. Okay, very good. And then we said we have a problem of degeneration, because when we raise a number that is lower than 1 to the power of n, lower or equal than 1 to the power of n, for increasing n, we get a degeneration, because there is a concentration of the probability. Okay, and we already discussed this, because there is here, after the exercise, we already discussed that if fx is 1, then fx to the power of n is 1, but is 1 concentrated on the max upper bound of the distribution, which may be infinity. And then if fx is lower than 1, then fx to the power of n tends to 0. And then we said, okay, we have to rescale it. With a simple rescaling, we avoid this problem. Very good. And in fact, with the rescaling, the probability of the rescaled variable, which we now indicate with the symbol z. So the original variable was x. And remember, capital X means the random variable, like the daily river flow of the Po River. It's the random variable, which can assume different values. The specific values of the random value, capital X, is indicated with lowercase. Let's see if it works. So this is the random variable, okay, which gives a population. Okay, the random variable has a population. Population is the pool of all the possible outcomes. Okay, if X is earthquake intensity, it goes from 0, it's lower bounded, and then the max is infinity because there is no upper value at the earthquake intensity, okay? And then this range of possible values is called the support. We said support is, in this case, 0 included, infinity excluded, earth excluded. Let's not say. I think the blackboards were working better.
I think it's supposed to use this. Yeah, doing the. No, like plain.
I think it is the same.
No, I mean to write. I think yes. Thank you. That's what's the.
Yeah. Good. Even if, okay. Okay, and this is for airplane, okay, airplanes. If it is a river flow, same thing, the river flow goes from 0 to infinity. Okay. So if I with the simple lowercase x, just put the ring here, you have to find it lowercase, but here you see that there is no wing anyway. And this is a specific thing. So it's a specific outcome. Specific outcome. Very good. Now, the escape variable now is called Z. Perfect. And therefore, this the probability of Z converges to this value with a simple transformation of variables. You get this, and in the power of n is the water generated. Okay. Okay, very good. Now we studied the theorem. We mentioned the theorem, the Fisher-Tippett-Gnedenko, and then this is the shape of the probability distributions that we get. And here I changed the symbol because, as you may remember, at the end of the lecture, I realized that there was X here. It's not correct. Now I have to use Z. And then you can recognize here the Gamma distribution. Okay, the Gamma distribution, I think you saw it in this form. So it's GB. Let me use, let's use not G, but P, X. So let's refer to X again. You saw it in this form, E to the power of minus E to the power of minus X and minus, let me use a symbol X minus mu. Divided by sigma. So you saw it in this form, and it's the same form that you see there after the scaling. So you understand also now what is the meaning of the scaling, and and you understand why you understand what is the meaning of the scaling, because precisely the fact that the Gamma distribution gives the probability not as a function of x, but as a function of x that is rescaled. So the location is corrected and the scale parameter is corrected. It means that indeed we need this rescaling. Okay? So let's say this is an inductive way of introducing the scaling. The deductive way is what is demonstrated there, that we need it, otherwise we get a degenerate distribution. The inductive way, starting from what is the real expression of the Gamma, anyway, confirms that we need to scale. And remember one thing, I am adopting these symbols because I refer to a literature, and also I browsed over the web. There is most of the literature uses these two symbols to indicate the correction of the scale, mu, and location mu, and the correction of the scale sigma. But remember that mu is not the average of the distribution or the mean value, and sigma is not standard deviation. They are related to mean and standard deviation, but they are not mean and standard deviation. And I want to make the specification because there is part of the literature that is using MOVE typically to identify the mean value of a distribution or the mean value of a population. And sigma is frequently used to identify the standard deviation. In this case, these are the parameters of the kind of distribution. These are those that are indicated with the symbol Mn and Bn there. But I didn't want to keep the same symbols because it's actually is Bn and An. I didn't want to keep the same symbols because it's a bit it's introducing another index. I prefer to refer to the large body of literature that uses the symbols. And this is for the Gamble, which is something that you already know. And then the Gamble has support from all the real numbers. Okay, then there is a table later on to summarize this. Frechet is a distribution that is called also type 2, is heavy-tailed. Gamble is light-tailed. Okay, so it means that the tail is long, but it is light, so it is quite close to the horizontal axis in the density graph. So this is a light tail, and this is a pattern tail. Okay. This is a heavier tail. Okay. The Frechet has a heavier tail, and this is a CDF. It's first of all, it's lower bounded. Okay. So probability 0 for any value that is lower than 0. And then it's quite easy to be understood because it's quite easy to be remembered, but don't remember it. And my suggestion for you, remember the Gamble because it's something that you already used, and we need to remember by memory at least one probability distribution. The Gamble is nice. It's used in many applications because it also can be easily inverted. So you can easily quantify, compute the quantile for a given probability. And then we have the type 3, which is the Weibull. The Weibull is upper bounded, so it's usually used to describe minima because it is upper bounded. And you see that probability, it's for negative numbers. And this is the Weibull. So the Fisher-Tippett-Gnedenko theorem demonstrates that if you get the maxima, you get one of these three distributions. Very good. Now, the last thing that we did is to specify the Gamble. It can be proved, but we don't want to prove it. The Gamble arises when the original variable x, from which we take the maximum, is exponential, normal, or gamma. And for instance, it is frequently used, the Gamble, to model the temperature and maximum rainfall. Okay, and then these are the other distributions. The Frechet arises asymptotically. Remember also the asymptotical dependency. The Frechet arises from Pareto Cauchy. We don't know these distributions, and we don't need to look at the formulation. It's a mathematical relationship which is not particularly difficult, but we don't need to look at it explicitly. Just remember these names because it gives you, when you talk to people, some knowledge in order to understand what they are talking about. And then the student T, it's another distribution. And examples, financial stresses, insurance losses, you see that it's a relevant field, and the Weibull, okay, arises from the uniform distribution, and beta, it's beta is another distribution. The uniform distribution, I think you know it, is just a distribution that spreads the probability uniformly over the range of data. And then there is any distribution with an hard upper limit, for instance, the maximum strength of a material and physical limits with strict caps. Okay, very good. Now, let's now look at the GAD, because this is indeed the distribution that it's most nominated, generalized extreme value. And it's a mathematical formulation that puts together, as special cases, Gamble, Feynman, and Frechet. Okay? And don't remember it by memory. I mean, you can easily recognize here the Gamble, okay, if the third parameter C is 0. So remember, this distribution has 3 parameters. The number of parameters of a distribution is a relevant feature of the distribution. What is the meaning of parameters? To adapt it. Okay, so depending on the temperature or the rainfall that we want to model, we calibrate the parameter in a way to adapt to the distribution. And of course, the larger the number of parameters, the larger the flexibility. This distribution needs to be adapted. And parameters are like tuning buttons of the old radios, in tuning. And of course, the larger the number of tuning buttons and the larger the flexibility that you have. On the other hand, so one may say, well, so let's take a distribution with a lot of parameters, of course. On the other hand, it is quite obvious that if you have a large flexibility, which means that the distribution can take many different shapes. Okay? So if I look at the probability density, I mean, this can be really, if I look at all possible shapes, it's very large. And then this means it's quite obvious that when you extrapolate, so you want to get your estimate here in a region that is not covered by observations. When you extrapolate, of course, any different shape gives a different value in extrapolation. So the question becomes, what kind of shape should I transform on? It means that uncertainty is increasing. It means that, for using a very technical term, the model with many parameters becomes less robust. What is robustness? Robustness means that the model is not really the best one, but it's the safer in terms of certainty of estimation. When you listen to people saying, use a robust method, please, you understand what it means. Like, use a robust car. What does it mean, a robust car? It means that maybe it's not a supercar, but I'm sure that I reach the destination. Maybe it's sometime later with respect to a super fast car. A Formula One is not fast. The Formula One, you make just a small kind of bad tuning, and then it crashes.
Yes.
Sorry?
Yes.
The Fiat is robust, yes. I mean, or sometimes we say all cars were more robust because maybe that they have problems, but you could fix it very easily with just a small, just some handy tools. And modern cars are more reliable, are more performing, no doubt on that. But when you get a problem, then you need a supercomputer in order to solve the problem. So regarding our discussion, this GEV has 3 parameters. So one parameter more with respect to Frechet or Gamble and Feynman. And the third parameter basically is introduced because when we want to make RIPS, we want the model, we want more flexibility. And therefore, this is the reason why it is included. So if you get the C equal to 0, then you get the Gamble, which has 2 parameters because C is 0. And then for given values of Xi, you get the other formulation, the upper one. Again, you don't have to remember it by memory, which gives for particular values of the parameter converges to Weibull and threshold. Let me just check one thing. Yeah, please, your question.
In this case, where you wouldn't be sure
Mhm.
which path you would decide to use, couldn't we do the same work we used to do in previous semester where we assemble?
Yeah, we can make an ensemble of predictions. Yes, this is possible, and it is done sometimes. And then the question becomes, how do you set the best estimate? So it can be the mean of the sample, but we discussed what is the problem if you take the mean of the sample, or it could be the safest solution. So if you don't have any problem with overfitting or with oversizing, you may take the upper estimate, for instance, for earthquakes, and you could take the upper intensity, provided that you don't have any problem in oversizing, because usually when we take the most prudent, the most conservative design, yeah, we get something that we get a solution that is not doable because we don't have resources for it. Okay, so the GAV, remember, generalized extreme value, it is recurring. And sometimes indeed it is used in the three parameters formulation. And people know that it's more flexible, maybe more reliable when you have a lot of data to support the calibration of the parameters. But people also know that when the number of observations is reduced, then it may be subjected to larger uncertainty. By the way, another thing that people know, and we could check it, is that the Gamma distribution usually overestimates the extremes. And this is something that you may say, but why? Because indeed, I also asked myself why, because the tail is lighter. But actually, what happens is that indeed, depending also on the parameterization, you see that we have different parameterization methods. The Gamma distribution, usually, it is also adopted because we know that leads generally to an overestimation. Okay, now, this is a summary table. It's like this would use the shape. So if you get these conditions, then you convert to Gamma, a shape or binary, and it also verifies the support that works. I think that they shouldn't use any compatible with the back because it works. But on the other hand, once that you start using it, you have to always use it. It works. Okay, so we get this summary table. Remember, what you read here is just an extension to several blocks, but it doesn't give anything more. The extension is done, I included it because here we refer to only one block. When we define the maximum, we refer to only one block. Okay, we said, let's suppose that we have a block of data. Actually, what we do usually, because we need a lot of data, so when we have a long sequence, we can split it into many blocks. And this is what we do. Typically, the annual maximum method splits the series in years. And then you take the max from any year. And therefore you get a lot of observations. Okay? And then you can compute indeed estimate distribution. This is what it's said here. And it is like the single maximum case, but the extension, I put this extension here because actually you need, in order to estimate distribution, you need more observations. So you can't use 30 years data, take only one maxima and estimate the probability distribution. You need to split in 2 years and then you estimate the probability distribution. But in this case, you are assuming that nothing changes in the period. So indeed, there is an assumption of stationarity because you are computing the average state parameter over the window of 30 years, and therefore there is this assumption of stationarity. Okay, and so what is written here is precisely this thing. From the above treatment, we understand why the random variable for X needs to be identically distributed here basically. And what if the data are not independent? Identically distributed means an implication of stationarity, because the probability distribution doesn't change. And what happens if the data are not independent? Because remember, we started from this assumption, IID. And I said, get familiar with this definition, independent and identically distributed. So what if the data are not independent? Because if we analyze weight data, wind data, snow, precipitation, they are not independent. They are time series. They are not independent. And of course, there are time series that are more dependent than others, like temperature has a strong dependence. So what if, when we want to analyze the annual maximum temperature, and they are not independent? Now, it can be proved that if the dependence is weak, then that's fine. I mean, we can, and you understand why. Because by taking the annual maximum, basically, you already remove part of the dependence because you are not taking data day by day. And therefore, if you have a weak dependence day by day, when you take the annual maxima, the assumption of independence of the sample that you then analyze is more supported, is more valued, it's more easily met. So basically, the conclusion is if you have a condition of fairly satisfied independence in the block maxima, maybe that you can look at the correlation and the dependence of this data. And if it is very low, that's fine, I mean. And what is the effect of dependence? The effect of dependence is that you need a longer sample in order to get the statistics. This is the effect of dependence. So if you need 10 data to estimate a gamma distribution, if the data are independent, if the data are dependent, then you need more than 10. This is the effect of dependence in technical terms. You are an engineer, so you have to know that, okay, the data are not independent. I need more. And you can easily understand by intuition this, because, of course, if you have 10 data and they are really independent, it means that they give you 10 different scenarios. If you have 10 data and they are dependent, then they give to you only an indication of one scenario. And therefore you need more, because if you have more data, then you can characterize different scenarios, but you need a longer record. This is the effect of dependence. So basically what we do usually when we estimate the annual maxima is let's look at the correlation. And I think you know what correlation means, how to compute the correlation coefficient into R. It's very easy. Into R, now I open an R window and you see it's very easy. So look at the correlation. When you analyze data, look at the plot because the plot is very important. So you see that there is something wrong. And then look also at the probability density, very important. And you know in R it's very easy to compute it. And then I'll show you in R how easy it is to compute to estimate correlation. And beware, if you see some correlation, then you need more data. And beware of this terminology we don't call it long-term persistence means a correlation that is not necessarily strong, but goes very far in time. Okay? And this means that indeed you need a larger sample for estimating reliably the extremes. Okay. Now let's look at, let's open an R window. Let me see if I'm still connected here. Yes, this is RStudio. Okay, and RStudio is, I'm not sure, I don't think we introduced it in the first semester, but it is, you can recognize here the R console, and RStudio is simply a platform that put together a graphical window with a console and with a window that allows to make programming. It's free to download, so it's free, the minimal version is free. It's commercially produced, but it's free, so you can download it, and you need R installed, but it is easier to work in R with RStudio. So
you introduced it.
Sorry?
You introduced it in the first semester.
Okay, perfect, but we didn't use it, correct?
No, you used
We used it, okay. Thank you for reminding me. So let's generate a series with the normal distribution. So R norm 10,000. If I only give the first argument, remember, it means that I'm generating from a standard Gaussian. Standard Gaussian means mean 0 and standard deviation 1. Okay. So, okay, let's forget about the warning. Let's see the plot. And I take the line because I prefer it. Okay, here you see the plot. So this is typically a Gaussian plot because you see the values are all concentrated around the mean. Perfect. This is just the plot. And you can see here that everything is fine. There are no outliers, it's okay. And then you can find the density, plot density, here 1, type equal 1, type equal 9. Hello, I think you sent a message, but I couldn't read it.
Yeah.
Okay.
Start to have me find.
Okay, I'm sorry for that because I couldn't read it because I was already teaching. Okay, I'm sorry. This is the Gaussian density. Okay. RStudio cannot be installed here. Actually, I'm working on my PC, so I could avoid it. Okay, perfect. ACF, here 1. And this is the ACF. What is the ACF? It's the autocorrelation function. And the autocorrelation function, now here it's not easy to see it because it's very. The autocorrelation function measures with an index that varies, which is the correlation coefficient from 0 to 1, from -1 to 1, measures the dependence between subsequent values of a time series. So what is the autocorrelation coefficient for lag 0? It's the dependence of any value of the time series from itself. So of course there is independence. And then it's 1, the index. Okay. The index again, -1 to 1. -1 means anti-persistence, means that when you get an high value, The next one is 1. So above average at the time 0, below average at time 1. This is negative correlation. Zero correlation means independence, or at least, let's say, for Gaussian data means independence, but I don't want to go into details. And then when we measure the dependence of one value from the previous one, then this is the correlation coefficient for lag 1, and 1 is here. And you see that it's almost invisible. And then you can increase the lag, dependence of the value today from 2 days ago. Lag 2 day, 2 steps, okay? And then you get number 2, etc., etc. And you see that it is anywhere close to 0. What are the dashed lines? This is the confidence span of the 0 value at the 95% significance level. So we talk about the significance level. It means that if the correlation is 0, you have a 95 probability, 95%, so 0.95 probability of getting the correlation coefficient within the bands. It means that you don't have to bother if you have 1 just outside, because it belongs to the 5% probability of getting a coefficient outside the bands, even if the actual correlation is 0. So basically, when we see that everything is more or less within the bands, it's fine. So you see, very easy. Okay. Now let me give you a counter example. And a counter example may be, for instance, let's generate into R a straight line with slope. Okay, so let me see if it works. We can put time equal a sequence from 1 to 100. Okay, so time is a sequence of from 1 to 100. And then we can say x equal time, let me see, a constant, like the constant may be 2 plus time multiplied by 0.5. This is a straight line, okay? And if we make a plot of x, you see it's a straight line, okay? Now, ACF of x, let's see what happens. You see the correlation, okay? Because of course there is a strong correlation. And there is a strong correlation, but now let me make this experiment. So instead of generating in this way, let's put a Gaussian random variable independent. So it is R norm 100, 0, 1. Okay. So now if we make the plot of x, you see that there is more dispersion, but still they are very correlated. Okay. Let's see the autocorrelation. Still very strong. But now let's make this change. Let's increase the variability 10. Okay, I increase the variability of the random variable. Now, if I make a plot, there is still some correlation, but not so strong. And then you see that the decrease. Okay, and if we want to exaggerate 100, then you see that the correlation is almost 0. Okay, and so this gives to you an understanding of I am analyzing the maxima. Let's see if they are correlated or not. And it gives to you a clear understanding. And then you can estimate the probability distribution anyway. Because we look at it, sometimes we need to design, and then we need to get a number. But we have to be aware of this. And sometimes it's just enough to get a perception of certainty. If you cannot quantify it, anyway, with some perception, you can manage. Okay, Perfect. Now let's go back. And let's move to the next one. Peak over threshold. Okay. Peak over threshold. First of all, let me remind you what it means. I go back because we already introduced it. This is annual block maxima, annual maxima. Okay. Block maxima, once again, I split the data in block of equal size and I take the maxima. And this is the peak over threshold. I fix a threshold and then I get the data above the threshold. And the purpose here, but we already discussed it, is to identify a proper value for the threshold such that the data that are above the threshold are fairly independent. And then, on the other hand, to select a threshold value, a threshold level, that gives to me the opportunity to pick up a lot of data, not just a few of them. Okay. Okay, now let's look at the peak over threshold, because you understand that the treatment must be similar, but on the other hand, it's not like the same thing as selecting block maxima. So must be similar, but with some difference. Okay, so let's see. The difference is indeed is just in the limiting distribution. And first, remember that we are now modeling the value over the threshold. So now we call our random variable y, and it's equal to x, where x is the population of the peaks, minus the value of the threshold. And there is a theorem, which is analogous to Fisher-Tropsch in ECHO, which is the Peakland by Kema-Dehaene theorem, that proves what is the limiting distribution for y. And the limiting distribution is called generalized Pareto. There is a link here to Wikipedia, and if you want more details, this is the generalized Pareto, and you see that there are several figures, and it explains how it works. Generalized Pareto is distribution that is very well known, is derived from the Pareto distribution. Okay, Pareto. Pareto, there will be many entry, Pareto distribution. And Pareto distribution is a power law probability distribution. So it's not an exponential distribution. What does this imply? Power law means that the convergence of the probabilities, and you see here there are several different parameters, the convergence of the probabilities to zero is governed by a power law, not an exponential. What does it mean? It means that the tail is fatter, because the convergence to zero of a power law is lower, the rate of convergence is lower with respect to exponential. Okay. It's much lower. And this makes the Pareto distribution distribution with fat tail. And I think here it's, we can go back. Sorry. So it's a generalized Pareto, which is given by this formulation. You don't need to remember it by memory, and it's a distribution with two parameters. Xi is a shape parameter, which gives the behavior of the tail, and beta is a scale parameter. And so the shape parameter describes the tail of the distribution. And I forgot to say this, for different value of Xi, you may also get a light tail distribution. So you have heavy tail when Xi is larger than zero. And then there is an exponential tail when xi is 0. And so you converge to a Gamble. And then for xi lower than 0, there is a bounded tail physical limits. Okay. So, and these are the tail probabilities. So the probability of x larger than, so basically this is the probability of y. Y is the exceedance above the threshold. We can also take, by introducing u as a third parameter, we can express the probability for x. But you see that in this expression, there is u. So u is a third parameter, which means the position of the threshold. Okay. Now, remember one thing in general, that is usually we in engineering, we use to express probabilities in terms of return level or return period. What is the return period? This is something that you have to remember, okay? And the definition, please remember it. There is also the link to Wikipedia, but it's just enough that we read here. It's an average time between events, such as earthquakes, for instance, for a given magnitude or higher to occur. So it's an average time between events that reach or exceed a threshold. Okay, this is the return period. So if I say the return period of an earthquake of magnitude 4 is 200 years, it means that on average, I imply that 200 years pass on average between two earthquakes of magnitude 4 or larger, Okay, this is the return period. Don't forget to say on average, because this is one of the most frequent misunderstanding of the return period. Like, okay, today I got an earthquake of 4, so for 200 years I am fine. I'm not getting any more. No, it is on average. So we may get next year an earthquake with a return period of 200 years, and then or may pass 1,000 years. Okay. You understand that the larger the return period, the larger the magnitude of the event. Okay. And why in engineering we use the concept of return period? We use it because, first of all, it is also adopted by several guidelines, and it is more effective in communication with respect to talking about frequencies or probability. So basically, probability of not exceedance for annual maxima of 99%, it means a return period of 100 years. I say again, a probability of not exceedance of 99%. So if I say the earthquake of magnitude 4 has a probability of not exceedance of 99%, the earthquake is not a good example because the earthquake is not prone to block maxima analysis. Let's say the river flow of the Po River of 10,000 has a probability of not exceedance of 99%, and I'm talking about the annual maximum flow. It means that the same value, 10,000, has a return period of 100 years. But it is much more understandable if I say, look, the annual maximum of the Po River of 10,000 has a return period of 100 years. It means that you get it on average once every 100 years. If I say chance of 99% of not exceedance of the annual maxima is less immediate. Okay, so this is why we use the return period. Actually, the return period under climate change is questioned because one says you cannot say it's a statistic, so you cannot say under climate change that you keep the same return period because for extremes we are expecting that the return period decreases. And my contribution to this discussion is you can still use the concept of return period. It's a return period that is changing with time. So it means that, okay, until now we have a return period of 100 years. For the next 50 years, the return period goes down to 80 years. And then from 2050 to 2100, the return period goes to 50 years. So it is a return period that changes with time, but still we can talk about return period. Of course, under the assumption of stationarity is much more understandable because, you know, a return time that changes with time, it becomes more complicated. And you see, in fact, what is written here. The reciprocal value of return period is the frequency of exceedance. Okay. And in fact, here there is a kind of imprecision because this is written the T here, right? The magnitude of the event XT satisfies this relationship. Okay. And actually, I would say that instead of writing T here, I should better write the T times 10. Because if we are talking about annual maximum, then it works in that way. So the T here return level corresponds to a probability of exceedance that is the inverse of the return period for the annual maximum. But if you take a peak over threshold, the distance between the points is not fixed, and therefore this doesn't apply anymore in this form, and we need to correct it. Okay. And I will, anyway, I think if we make reference to the annual maximum, the sentence is correct, and I think you understand it. So there is a direct relationship between the return period and the probability. And the way to express it, of course, changes depending on the time step of the data. Okay. And then if you use the peak over threshold and you assume that indeed you have a number of data that are above the threshold that are the same number of years as the years of observation period, you can write the probability, you can write the quantile, because this is the inverse of the generalized Pareto. This gives the value of the intensity of the event depending on the probability or return period. Okay. So this is the inverse of the probability distribution, which gives the quantile. The quantile is the value of the population that corresponds to a given probability. Okay. Get familiar with these terms, okay, the quantile, because then we talk about quantile plot later on. And so you have to get familiar. And I know that it's not so easy. When I was a student, you know, getting oriented in probability quantile, what is the quantile? And the quantile is, as I said, simply the value of the random variable that corresponds to a given probability. And then you get it by inverting the probability distribution. It is very nice when the probability distribution can be inverted. The Gaussian distribution cannot be inverted. You cannot get the quantile of the Gaussian distribution with an explicit relationship. It cannot be inverted. In this case, this one can be inverted. I will make a correction here because, as I said, this relationship is valid only if the number of observations correspond to the number of years in the observation period, the number of observations over the threshold. Okay, this is the difference between block maxima and and peak over threshold. Peak over threshold uses more data. Potentially, it depends on the level of the threshold, but it gives to you the opportunity of using more data for sure. Gives lower variance estimates. What does this mean? It means that the uncertainty, variance of an estimate means the uncertainty of an estimate. It's not only the variance defining uncertainty, there is also the bias defining uncertainty, which is a difference in the mean value that you simulate. But lower variance implies lower uncertainty. And why I have a lower variance? Because I can use more data. So this is why I get estimates that are less uncertain, and gives more flexible tail modeling. The peak over threshold gives more flexibility in modeling the tail, and it's better for irregular sampling, of course, because I mean, if you have one observation each day, that's fine, meaning that when you select the block maxima, it's perfect. Make a selection. It's I mean, I take the annual maxima if I have an observation each day. I take always the maxima from a sample which has the same size, 365. But if you think of missing values may end up with a year where I have half of the observations. Then when I take the max from half of the observations, so the blocks have an irregular size or an irregular time coverage, if they have the same size, then the annual maxima, the block maxima becomes a little subjected to additional uncertainty. While if I have an irregular sampling and I decide to take the peak over threshold, it's fine. I mean, I may miss some of the peaks where there are the missing values, but this doesn't have any influence in the estimation if the block is long, if the observation period is long. Okay, and then now we get into another exciting topic, how we estimate the parameters of the distribution. And there are several methods. We don't describe all of them, but I want you to know all of them, because at least to get an introduction, because each of the 4 methods that you see listed here has some advantages, some good points. So let's start from the most traditional one. It is the method of moments. It's the most traditional because it doesn't require a strong computational effort. So its use was motivated by the simplicity in earlier times. And let me introduce it to the blackboard. So, first thing, you should ask yourself this question: how many parameters do I have to estimate? So, first question, 1, number of parameters. Number of parameters. And of course, you look at the parameters of the distribution and you know the number. Why this is important? First, because it gives you an idea of the flexibility of the distribution, an idea of the uncertainty. But in our case, because now we are involved in fitting of the distribution, in our case, this means that by defining the number of parameters, I identify the number of equations that I give. Number of equations. Okay, so Campbell has 2 parameters. So that's Campbell. 2 parameters. 2 parameters, 2 equations. Parameters, 2 equations. Good. How to derive these equations? There is a very simple idea, which is equate mean of the distribution to the sample mean. To the sample mean. This is a very simple idea. What I want is that the distribution describes a population that has the same average, the same mean value as my data. So the gamma is from the annual maximum, I compute the average value is 100, okay, perfect. So I want a distribution whose population is the same mean value. And then I make 3 equate standard deviation of the distribution to the standard deviation to the sample, sorry, sample standard deviation. Why I select mean and standard deviation? Because the mean is the easy estimate. What do I mean with easy? It's easy to compute, but it's also subjected to a very reduced uncertainty. So it's obvious that I take the mean, because the mean can be estimated reliably even with a few numbers. So it's obvious that I take it. And then the mean is not enough. And then I look at the standard deviation. Why the standard deviation? Because it is computed by raising the data to the power of 2. So it's not at the power of 1 like the mean. Raising the power increases certainty, increases the number of data that I need to get a reliable estimate. But still, it's the power of 2, so it's okay. It's reduced. It wouldn't be reasonable that I take the skewness, which means data elevated in the power of 3. If you are not familiar with the concept of how to compute the mean, I'm sure that you are familiar. How to compute the standard deviation, I'm quite sure that you are familiar. How to compute the skewness, get familiar with this. The skewness is proportional to its computed by the data raised to the power of 3. These statistics that we compute, the mean by raising the data to the power of 1, standard deviation, raising the data to the power of 2, skewness, raising the data to the power of 3, they are called moments of the distribution, or sample moments of the sample. They are called moments with order corresponding to the power you raise the data to. Distribution is the mean of distribution. The sample first order moment is the mean of the data. So by equating the first order moment of distribution with the sample moment of the data, sample first order moment, I get the first equation. And then I go to the second order moment of the distribution, which is the standard deviation. For variance, remember, standard, it is the variance that is computed by raising the data to the power of 2. And then the standard deviation is the square root of the variance. Remember, these are simple suggestions to get oriented in statistics. This is very reasonable. Method of moments is very reasonable. If I have 3 parameters, then I take the third order moment. And then from this idea, you may wonder something like, why don't we take moments that have a kind of fractional order, or in order to avoid to go to the third order moments, is there a way to obtain a third equation without going to the third order moment? Yes, and this gives rise to bare moments. It's another method. So we don't go into details of this. I went into the details of the method moments. Just keep into account that the probability weighted moments and L moments, and there are also other kind of moments that have been recently proposed. These are statistics derived from the data without raising them to the power of 2 or 3. And this is why their moments are today very popular and very frequently mentioned. So use their moments to estimate extremes. Because if you have a distribution with 3 parameters, already the variance is, for standard deviation, is highly uncertain. If you take the skewness, which is the moment of third order, is very uncertain. So people say, take L moments, because L moments are additional equations, and we don't go into the details in order to get further constraints equations without raising the data to a power greater than 1. But let's focus on the method moments again. And here you see advantages, simple and intuitive method, reduced computational requirements, limitations. And first of all, okay, here there is a, sorry for that, I need to correct this. And this is the symbol Xi should have appeared here, okay? And what I missed here is a slash here and a slash here. Anyway, higher order moments may not exist for some distributions. Remember that, because for the GLE, for some Xi values, you don't get a third order moment. And this is a limitation, and also less accurate for tail estimation for the uncertain. Okay. And here I concluded by saying it's mainly used for deductive purposes of preliminary analysis, but not only deductive. I would say that for preliminary analysis and for base simplicity, this is very useful. Okay. And now we see, after the break, an exercise of application to the Gamble distribution, estimation of parameter with the method of moments. Why it is important that you understand it? I'm sure that you already know the formulas for getting the parameters of the Gamble, and these are derived from the method of moments, but it's necessary that we get the concept, because we can, by knowing the concept, we can then introduce better the other methods like maximum likelihood. Okay, but we discuss this later. And we can meet at 2:15, or let's say you are free. So let's meet at 2 if you are free at 2. So we start earlier and we close, we have 3 hours, so we make a 15 minutes break after. If we start at 2, 3:30, 3:45, we make a 15 minutes break, and then 3:45, 4:30 like in Ravenna. Okay. And definitely you prefer to come here. Yes. Okay, just 1 second that I close the recording, and then I take this opportunity to.
Oh, Professor,
Yeah.
I think they're having the same problem.